Good morning, everyone. I'll quickly introduce myself. I'm Lucas Raas, Business Development Manager for Bekaert in Singapore. I'm here today with my colleague Tom, who will assist me. Tom, maybe you can introduce yourself quickly.
Okay, thank you. Hello, everyone. I'm Tom. I'm a sales manager based in Thailand. Nice to meet you and warm welcome to join our webinar today.
So it's the first webinar about our Dramix Pro software launch for the slab-on-ground calculation tool. We'll have a Q&A at the end of this session, but you can always leave your questions in the Q&A section of the meeting, and we will handle them at the end of the webinar. So welcome everyone. What's on the agenda today? So we'll first have a short intro about Bekaert, and then to better understand the material steel fiber reinforced concrete, I will shortly explain what Dramix steel fiber concrete is, how the material is characterized, so how we go from a standardized beam test to the bending moment capacity of a certain cross-section, which is reinforced with steel fiber. Then we go over the design fundamentals, which give a better insight on the behavior of steel fiber reinforced concrete. And then come to the main topic of today, which is the slab-on-ground, so the different types and their main aspects and properties. And to end with, we will give a demo of the new calculation tool, and depending on the time we have, I do 2 or 3 design cases together with you. So first of all, about Bekaert. Bekaert is a Belgian company and is a global and technical market leader in material science, so in steel wire transformation. So what we do is we start with a wire rod of 6.5 millimeter, most cases, and then with certain different types of mechanical drawing or punching or cabling, make it to a lesser diameter, give it a certain profile, and then if necessary put on a coating like we do with the steel fiber. Sometimes we give it a galvanized coating to make it more corrosion resistive. Bekaert, by some key figures of last year. So we serve customers in over 130 countries. We are a company with over 24,000 employees. In 2023, we had combined sales of 4.3 billion euros. We are very, we think in innovation and sustainability are an important pillar within Bekaert. That's why we have quite some budget in R&D and a lot of patents going on. And for the sustainability part, we try to have as much carbon emission reduction as well in our manufacturing plants as in our materials that we buy for our different products. If we look all over the world, our manufacturing plants for the Southeast Asia or for Asia are mainly in Indonesia, India, and China. But as you can see, all around the world, we have quite some manufacturing plants and offices. For Bekaert construction, today I'll talk about the Dramix steel fiber, but we have also a different range of applications and products in our portfolio. For example, for road reinforcement, we have the mesh truck and Fortifix. For the masonry reinforcement, we have the Murfor Compact and the Brick Force, and then also the plastering reinforcement. We have Armanet and Stukanet for that type of applications. But today the focus is on the Dramix steel fiber concrete. So first of all, to begin with, it's the principle of concrete reinforcement is concrete itself is a brittle material, and it will, if it's unreinforced, will not have any resistance against tensile stresses. That's why we have to add reinforcement like mesh rebar of steel fibers to increase that, to give it a certain ductile behavior and have a capacity in the tensile against tensile stresses. Looking at steel fiber reinforced concrete itself, you see steel fiber concrete is it's steel fibers that are added to the concrete mix and are distributed homogeneously and 3D oriented into the whole concrete section. If you look at the left side, you'll see what it does to your concrete. So if you put a certain energy with a point load on an unreinforced slab, you will see that it will crack very brittle, and you can't take up that much energy. While when you increase the dosage of steel fiber, you'll see that your cracking pattern, so your ductility of your material will increase. You will give it a certain ductility and toughness, and also the energy that your concrete can absorb will also increase by using or by adding steel fibers to your concrete. So now, how is steel fiber reinforced concrete characterized? So to characterize your steel fiber concrete, we do standardized beam tests according to the EN 14651, which is a displacement controlled beam test with a specimen of 600 millimeter long and the length and width and the width and height of 150 mm. So it's a 3-point bending test where we make a notch in the middle of your beam. And that's the place where you measure your crack mouth opening displacement. So you measure how much that notch opens while increasing or while putting on a certain force. So what you will see is the result is a typical graph like this, where the first peak is the point of cracking of your concrete, and that's the moment that your reinforcement can come into play. So the first point or value that is important for our steel fiber reinforced concrete is the FR1 value, which relates to a crack mouth opening displacement of 0.5 millimeters. So this relates to very small crack mouth opening displacements. Later, you will see that this is also the value that will be used in SLS calculations when you do crack width. So when you do crack width calculations. Then also the second value that we use to characterize the material is the FR3 value, which correlates with a crack mouth opening displacement of 2.5 millimeters. This will be the more governing factor in ULS calculations when you allow larger crack openings. So the typical results, so the results we get are residual flexural tensile strengths. So because it's a 3-point bending test, it's a flexural tensile strength we get. Because one beam test for example, one concrete type with a certain concrete dosage, it's not sufficient to only do one beam test. It will not be representative. You need to do at least standard beam tests to have a representative test series. You'll see that a good test series will have a coefficient of variation between the 20 and the 30%. This is because it's only a small, if you look at the section, that is correct. It's only a small area. So if you have 2 or 3 steel fibers that are covering the crack, will also have quite a bit of a difference on your result. That is why the coefficient of variation between 20 and 30% is expected. So once we have that 6 beam tests, we can calculate average values, and then to use this in a calculation later on, we will have to use the characteristic flexural strengths, which are based on a normal or a log normal distribution. So as you can imagine, we have different types of steel fiber families. You can see them here at the bottom. We have the 3D, 4D, and the 5D steel fiber family. Visually, you can determine them from the anchoraging. So 3D has 1 hook, the 4D has 1.5 hook, and the 5D has 2 hooks. It's not only on the anchoraging that there's a difference, but also the tensile strength of the steel fiber will increase when you go from a 3D to a 4D and a 4D to a 5D. Why is this? This is because when you have a better anchoraging in your concrete, you will also expect that the tensiles, so the forces in your steel fiber, will increase because it's better anchored in your concrete. That is why we also increase the tensile strength of the fiber when adding this extra anchoraging. Looking at some typical results, you'll see that a 3D fiber is the most standard fiber. It's also the oldest one. It will have a behavior like this. So it's used in our most common applications, not structural applications also. While with a 4D, you'll see that the FR1 value is quite high, which will also be higher than a 5D fiber. So we'll see that this 4D fiber is commonly used in applications where crack control is governing. So in SLS, this will be a very good steel fiber. And then the 5D fiber is designed for applications, for very structural applications where you need a high FR3 value, where you need some kind of bending hardening behavior. And that's when the 5D fiber comes in play. But once you've done the bending tests, you have those characteristic residual flexural tensile strengths depending on the beam tests. To use this material in a certain calculation, you will need the sigma stress diagram of your concrete. So normally the concrete does not have any capacity in the tensile zone. You will also have a capacity in the compression zone. So in the compression zone, nothing changes, but you will have a certain capacity in your tensile zone as well. And to go from that residual flexural tensile stress, you will need to go to this sigma stress diagram, which is a uniaxial tensile stress diagram. And for that, to do this, you will have some conversion factors. You will have material safety factors, size factors, and hyperstatic factors. All these type of factors are depending on the standards and norms you're using. These are all incorporated in our design tools. If you want to go deeper into that, you can ask us separately, because this depends on the country you're in, depends on which standard or norm you're using. So that is something we will not go deeper into this in this webinar. But if you have questions, please ask them in the Q&A or contact us after this webinar. Then if we look at how can we calculate a cross-sectional moment capacity, If we look at the stress strain diagram, you'll see here you have your compression zone of the concrete. You have then indeed that capacity of your steel fibers, which you will see the sigma 2D depending on FR1K value, because this is right under your neutral axis where the crack width or the crack mouth opening is very limited. So that's depending on the FR1 value. And then sigma 3D is at the bottom of your section where you expect much higher crack widths. That's why it's depending on the FR3K value. And how can you calculate then the bending moments? Is just like when you would have it with only steel mesh, you just write down your moment equilibrium, your cross-section equilibrium, but instead of only having the compression zone of the concrete and the tensile zone of the reinforcement, if it is there, you will also have that third factor, which is depending on the FR1 and FR3 value that you reach out of your beam tests. So that's shortly how the material is characterized. Now go over to the design fundamentals of steel fiber reinforced concrete, which give us indeed, as I told, a bit more insight in the behavior of steel fiber reinforced concrete. So first of all, it's important for us to, if you look at those displacement control bending tests, which is an isostatic system because it's a beam test, a double supported beam test. If you look at plain concrete, you'll see that once you reach your point of cracking, you have no capacity left, and your beam will just fail. So you have there's only use in compression. If you go to reinforced concrete and you have more than the minimum amount of reinforcement in your beam, you'll see that after the first point of cracking, you'll have a certain capacity, capacity that is higher than your first point of cracking. That is what we say is a bending hardening behavior. And for the steel fibers, you'll see that there is a certain capacity left because it's displacement controlled. You can also visualize this, but it will be in the steel fiber mixes or the steel fibers we use in slab-on-grounds. This behavior will be mostly that the post-crack behavior is lower than that first point of cracking of your concrete, which is called a softening behavior. And why is this important? This will make sure that so that in an isostatic system, the steel fibers are not that interesting to use, but in hyperstatic structures where you have redistribution of bending moments, there the steel fibers come into play. So this is again looking at the different types of loads you can have. So if you have uniaxial tension, when you have a softening behavior, this will not you will not have any capacity left, while when you have a hyperstatic system, you will have the capacity to redistribute loads, and there it is indeed beneficial to use the steel fibers. Again, I will so why it is important to distinguish isostatic and hyperstatic structures? It's because when you look at an isostatic structures like a cantilever beam, for example, as soon as the section fails, your whole system will fail. So this means that there's no redistribution of loads possible. So your system and your section capacity are the same. While looking at a hyperstatic structure, for example, the Eiffel Tower, when one section would fail, this does not mean that the whole system will fail. You will have a redistribution of the loads in the structure, which means that your system capacity will be larger than the capacity of one section. And that's actually also what happens with a slab-on-ground. It's a multi-hyperstatic application or structure. So that is why steel fiber reinforced concrete is very advantageous to use there. To visualize this a bit more, we'll go to for example, to the mode of failure for a plain concrete is when you put a certain load on it and you reach the point of cracking. For a plain concrete, you will have a brittle crack and there's no capacity left at this section, so you will not have any redistribution of loads anymore. While if you look at the steel fiber reinforced concrete, when you have a point of cracking, you will have a certain post-crack capacity at that section. So a plastic hinge will be formed at this location. And then you can increase your load even more until at the right and the left side of your first hinge, you will also reach the section capacity and a second crack will occur. And that is only the moment that your plate will fail. And that's the difference between that. That's why it is important that we look at the system performance for slabs on ground and not only at the section performance. Because in that way we can optimize the amount of reinforcement, so we can optimize the steel fiber dosage, and we can also take into account the strain softening behavior and the redistribution of loads when using the steel fibers. How is this done in our design tool? So first of all, you have two ways of determining the occurring bending moments, which is first of all the linear calculation, which is just a FEM calculation, which doesn't consider any redistribution of loads or bending moments. When you only look at the section capacity, so that's for when you would use steel fibers. In that case, that's a really conservative design approach for steel fibers, while using plastic calculations like the yield line theory of Loosberg, which is used in our Dramix Pro design tool, there is this allows to redistribute the loads, and so it also allows to use the bending softening behavior of the steel fiber reinforced concrete. This yield line design approach, it's a very iterative and plastic calculation mode, which takes into account a lot of influencing parameters, which you will have to incorporate in the design tool. So this is for example, the soil characteristics, the geometry of the slab, the dosage of the fibers, the concrete class. It's all depending on those factors. And it's also important, of course, to consider all load situations. Like you need to consider UDL loads, you need to consider point loads in the middle of the slab, near sockets or joints or near edges. That's all things that are considered in in our design tool, as we'll see. So now to go to the slab on ground. So first of all, give short introduction in the three types of floors, industrial floors that they are. So in a standard industrial floors, we need to give a certain contraction joint, type of contraction joint, to minimize random cracking. The most effective and known way to do this is socket joints. Like you see here in the picture, a socket joint. A conventional socket joint should be 1/3 of the total thickness of the slab. It cannot be too deep, because then you lose the load transfer at the socket, but it can also not be too shallow, because otherwise, again, you can have that random cracking. The advantage of sockets is that it's a very straight and clean cut. It's very known. It's a very cost-effective way of building an industrial slab. The disadvantage or the problems you can have with a traditional socket floor is that those sockets can start to deteriorate after a while when there's a lot of reach truck traffic on it. You can have the rocking of the slab or the spalling of the joints, which eventually leads to a lot of maintenance cost to your slab. To counteract that, there's the second type of floor, which is the jointless floor. So these types of floor do not need any sockets anymore. You will need special joint profiles at larger distances up to 40 or 45 meters, which allow your concrete to shrink. Those contraction joints looks like this. So they have some kind of dowels to make sure that there is enough load transfer between the two panels. And they also make sure that your concrete at the location of the joint is protected. You also have these types in the sinus and cosinus profile to limit when a reach truck is driving over to limit the effect on the driver. Important for this type of floors is that the execution needs to be very good. You can't have any restrained points of restriction, because once you have a point of restriction there, your slab will start to crack, and once your slab cracks, you don't have any failure mechanism anymore to counteract that cracking. So you will need to have insulation material around columns and against the walls to make sure that your slab is free to shrink. You'll need additional reinforcement at edges, and you will also need 1 or 2 PE floors to minimize friction to make sure that your shrinkage can take place in those contraction joints. Then as last one, you have the seamless floors, which do not require any sockets or expansion joints anymore. Why not? Because they are a combination of a top mesh and steel fibers. Why we use the top mesh? This is to take into account restrained friction shrinkage. So we really do a crack width calculation based on the combination of the steel fibers and the top mesh. So this means that in the effective zone around the top mesh, your crack width will be limited to most of the time a 0.3 millimeter. If your slab, if you have a larger slab panel, for example, with those seamless joints, you will need to have multiple pouring days, and to make sure that you don't need a contraction joint at those pouring joints. You can make sure that because the steel fibers, the network of steel fibers is not continuous over here, you will need to add some top and bottom mesh to make sure that at the location of your joint, you still have the same bending moment capacity and the same crack width control as you have over the rest of your flow. But this is only, for example, this is 1 to 1.5 meter in total. At that contraction joint, you will need an additional bottom mesh and some additional top reinforcement. So here you have a quick comparison of the different flooring types. As you will see in the demos later, we will not go to the seamless floor design, because for these type of floors, you also need, as I mentioned, the crack width calculation, which is not incorporated in the design tool just yet at the moment. So if you would like a calculation or a design of a seamless floor, you can always contact me or one of my colleagues in the region to make sure we can do this type of this type of calculation. So now we'll go to the demo. Go to the website or CEP, which is our customer engagement platform. Looks like this. So it's on our, if we go here to the software tools, the Dramix Pro is the discover the tool. This is the location where you can, if you don't have an account yet, you can register and you can get an invite to the Dramix Pro tool. Let's log in. If you look at the tool, it's the first thing we need to do is add a folder, which we can call test save. Oh. Example. So test, we create a new project. On this project form, you will need to enter some detailing. I will start with a socket floor. Are all locations where you have that blue asterisk, you will need to fill in some information to make sure that you can find your different projects back. Tests. You will also need to make put your email address. That's because when you are when you request a design note, the design note will be forwarded to your email address that you mentioned here. And then we'll use the International System of Units and the EN, so the normal European concrete code. So you save it, you can go next. For the first demo, I'll go back to the slides. We'll do a lightly loaded socket floor, where you have, first of all, the pallet racking of back-to-back racking systems with wide aisles. So you have 4 point loads of 30 kilonewtons with a distance of 1 meter, 30 centimeter and 1 meter, and the base plate of 10 by 10 centimeter. What will also be important to incorporate the load case is the racking system at the edges, which are 2 point loads on a which are placed very close to the edge of the slab. So from the edge we take here 300 mm. So if we go to our slab-on-ground tool, the first thing we do is we can take an approach depending on the country we're in. We'll keep it this now, the Bekaert slab-on-ground, the standard method. But if you are, for example, in Germany or in Sweden or somewhere else, you can take a different approach of calculating. You can also take some country depending settings, which are different for each countries. I will keep this at the standard. The concrete age of loading, which is normally 28 days, will not change this. This can be changed if you like, but 28 days is the normal way of working. If you then look at the safety and the load factors, these are all based on the approach and the country depending settings you just choose. So for steel fiber concrete, this is 1.2. For your concrete and your steel, this is the normal 1.5 and 1.15. For the load safety factors, because we are designing industrial floors, we can use a consequence clause, which is 1, because it's not part of your foundations. It's not a structural slab. It's only your industrial floor, which is fully separated from your supporting structure. That's why we use lower load safety factors of 1.2. And we can also add the dynamic load factor for the wheel loads. Then we go to the structure. So we can choose here between screed, socket, heavy-duty pavement, jointless, and combi slab. I'm here in the advanced version. To begin with, you get access to a non-advanced version where you can only use or design socket floors, but you can ask for the permission to use the extended version as well if you want to also do the design for a heavy-duty pavement of a jointless floor. As I mentioned, the combi slab, it's different because you will need also there an SLS calculation, which is not yet possible with the online tools at the moment. But if we go to a socket floor, an indoor socket floor with tempered ambient conditions, for example, we have a 15 millimeter socket floor, socket 6x6, with a panel ratio of 1.5, for example. So this means that your maximum socket length is 6 meters, and you can have panels up to 6x6 or 4x6. Then you can have doweled joints, which are the contraction joints. If your floor is too big to cast in one day, you will, besides the sockets, you will also have doweled profiles to make sure that you have, that you can limit that. You can limit your panels by for the day pourings. This doweled, this load transfer efficiency, this is a default value which we take at 0.8 for the doweled profiles. This is a conservative value, the 0.8. If you know which profiles will be used, you can ask this to the manufacturer of the profiles if this value will be higher or not, because this can have an effect on your design. And then we'll start with a fiber-only reinforcement, and of course the soil model, which is depending on I'll show you on the some tests that are done on the subbase. So here we would go for a K value of 0.03, which is based on the plate bearing tests, which have to be executed before on the subbase of your floor, which with base plates up with a large diameter base plate of 750 or 762 mm. For this design, we take into account the 0.03. And in some cases, like for freezers, sometimes you have insulation underneath your slab, but in this case, we will not take this into account, but you can also incorporate it in the design. For socket floors, we most of the time will take one layer of PE foil to also minimize the friction with the subbase. And for the materials, we'll use a concrete C2530, and here we will use the 40-65-60, which is a 60 millimeter fiber with a L/D ratio of 65, which means that your diameter of your fiber is 0.9 millimeter. We'll start with a dosage of 25 kilograms per cubic meter. Then we can go to the loads. As mentioned, we only have racking loads, so we'll start with the back-to-back racking loads. So we had a racking load of 30 kilonewtons. This is like this, so it's 4 points in line, which is the back-to-back loading situation, where the width or the depth of the rack is A, which is 1 meter. Distance B is the back-to-back distance, which was 300 mm. And again, C is the depth of the racking, and with the footing plate of 100 mm on 100 mm. The next thing we need to take into account is the positioning of this back-to-back racking. So you can have, what you see here is the dotted line is a free edge. So the thing is, you can't have a back-to-back racking at the edge of your slab. If you have it, for example, here at the edge, your point load there will be only 15 kilonewton, and this will not be governing anymore. So you cannot have it like this next to your free edge. You can also not have it perpendicular, because then you would only have 2 points in line and not a back-to-back system anymore. But what you can have is next to the socket, it can be standing on a socket or next to this one. So the blue lines are the joint type 2, which are the sockets, and the joint type 1 is the contraction joint. There, the different, you can have those point loads standing very close to them. And also at the corner of 2 sockets, you can also have this load situation where the back-to-back racking is standing. Then, as mentioned, for the 2 points in line, this can happen perpendicular to the side. You not have to incorporate all the rest, because the back-to-back will be more governing compared to the 2 points in line. But for the free edge, you need to incorporate this one. So there again, you take the 30 kilonewton, 1 meter, the depth of the racking, and then put it, the size of the plates of the base plate is 100 by 100. And the load situation, like I mentioned, you take it at 300 mm from the edge of the slab, because it's a footing will never stand really at the edge of the slab. So now we have the point loads. You can also incorporate wheel loads, like, for example, what you can have here is point loads of reach trucks or lorries. So, for example, a reach truck type FL3, which has a wheel load of 31.5 kilonewtons, a wheelbase of 1 meter, and a wheel pressure of 5 MPa, because the wheels are full. It's not air, it's full rubber wheels. And then for a lorry, for example, you can have quite a heavy lorry driving into your building that needs to be emptied. So in that case, we'll take a lorry of an axle load of 190 kilonewtons with a wheel pressure of 2 MPa. So those are the 2 load cases we will enter into the design. So first of all, 1 axle, 2 wheels, which is the reach truck, 1.31.5 wheel load, and a wheelbase of 1000 millimeter, wheel pressure of 5. The load position, you can imagine that this type of reach truck can drive all over your slab. And the second is the very loaded, the highly loaded lorry. So the axle load of the lorry, which can also drive everywhere. For example, when it drives into your building, it will be the load situation where it is next to your, when it's driving over the free edge. So there you have the 47.5 kilonewton. It's 320. This is mentioned in the Eurocode 1, the distances, the standard distances between the wheels is mentioned over there, and then an MPa of wheel pressure of 2. Load position, it can drive everywhere. So that's what we incorporate in the design. And to end with, you can have sometimes some pallet stacking, where you have a UDL load of, for example, 30 kilonewton. And if you don't know if it's several defined block or a one single defined block, you can do the worst case, and then it takes into account, it goes on an iterative way. It goes looking for the most, the worst case scenario between the loading area and the distance between 2 UDL loads. So now we have not taken into account the line load. So now we have incorporated all the loads, if we go to our results, so you can click on view interim result. You'll see that there's the wheel loads are more than 100% used of our capacity. We can have a look, if you calculate the final result, we can have a look where this, what load case is governing. Go there, we'll see it's the bending at the wheel load. So we can go to wheel load and see that here. So it's when the truck is driving in, you have your error where the wheel load is too high. Also at the corner of the secondary joint, which is a socket joint, it is becoming a problem. So to solve these two, we can just add, I will show you the previous one. We can add some at here at the fiber only design. We can add some, you don't have to increase the fiber dosage for your whole slab. If the governing load factor is only at the free edges, then you can just incorporate some top reinforcement. So then you do it like this, 6 millimeter over 150 at the free edges, for example. Then you will see we'll have to make sure that everything is back in place. It's still a small glitch in the system, but it will get out of it. So if we look at the end results now, you see that your reload is brought back to 80%. So only by adding a bit of additional reinforcement at the edges, at the free edges, you will make sure that you don't have to increase the thickness of your full slab or the dosage of fibers for your whole slab, but you only will need some additional reinforcement at the free edges. So if we go look now at the wheel loads, you'll see here at the free edge, your capacity is only used for 80% now at the moment. I'll go back to the slideshow. So this is a way of calculating, for example, a socket floor. So what is the result then? It's a 150 mm slab with C2530, 25 kilo over 406560 and sockets every 6 by 6 meter. And then where your lorry drives in, because that was the most governing load, you just have to place at gateways or when it can be driving close to the edges, you have to place some additional mesh, which we introduced was a 6 by 6 150 at the top. If you see here, if you put next, you can ask for a summary printout or an extended printout, which will be sent to you by mail. So it will look like this. So in that printout, you will see that you'll have you will find back all the factors that are used, all the data you have put in. So the 150 slab, the amount of fibers, the concrete class, as well as the load safety factors and the material factors, the additional top reinforcement that is required, the characteristic of the soil properties are also incorporated, the types of joints you use, and then the different load cases like the point loads of 30 kilonewtons of the racking system, the back-to-back, the wheel loads of the reach truck, the wheel loads of the lorry. They're all incorporated in this one, the UDL load. And then you have the capacity of your slab, of your steel fiber reinforced concrete, as well as the combined reinforcement where you have the top mesh and the steel fibers. This is all incorporated in the design node, and then the different load cases you have selected. So here you can see an overview of the different load cases where you have put them. So next to the dowel joints, next to the sockets, if they're incorporated or not. This is all indicated in this table. And then you have your overview of the calculations all underneath it, and a quick summary at the end of your design. Then I will look at time-wise. It's almost it's 20 past 11 already. We'll do one more design case, and then we go over to the Q&A. So if you have some questions, please put them directly in the Q&A until now. For the second design case, we will look at a jointless floor with a very narrow aisle racking system with high pond loads up to 120 kilonewton. You'll see that once you try, if you would try to do this type of application with the socket floor, you will never be able to reach it because sockets are a very weak point of your floor. And if you have a point load up to 120 kilonewtons back to back, close to a socket, that will not work anymore. So that is why for this type of application, we will go to a jointless or even a seamless floor. But for the second example, where you will do a jointless design of a VNA. So going back to our project, we can create a project again, call it jointless floor. So we will do a jointless floor, customer name. Oh,
hello,
Lucas. See my screen. Oh, you lost my screen. Yes, yes. Sorry.
Please. Thank you.
Sorry. So sorry again. I will show it again. So for the second load case, we'll do a jointless slab of a very narrow aisle. So with point loads up to 120 kilonewton. Closer back to back, so only 200 mm spacing between the back to backs, and base plate 120 mm. Reach a UDL load of 50 kilonewton per square meter of stacking pallets, and a reach truck of FL4, a bit higher reach truck, which can take up a bit more loads. So a wheel load of 45 kilonewton, wheelbase of 120 mm, and again a wheel pressure of 5 MPa. And then a double axle lorry, if this needs to be loaded inside, we'll also add it with 2 axles very close to each other. So we'll start again with a new project, call it jointless floor. It's again a test. We'll use the same concrete code as we did before, so we can save, go next, again use the slab-on-ground. We'll keep here the same design approach, again with the settings of a consequence class 1. We'll start with, because of the high loads, we'll start with a jointless floor, 180 mm thickness, panel size up to 40 meter. We will make sure that the maximum panel ratio will use 1.2 because we want our panels to be as square as possible to make sure that you don't you limit your shrinkage stresses. Again, keep this the default value. Start with a fiber only. Because of the high loads, we will ask for a better subbase, so with a K value of at least 0.05. And because it is a jointless floor and we want to minimize our friction, we will use 2 layers of PE foil instead of 1. For the material, we'll use again a concrete class C2530 and a 408060 BGE, which is a better performing fiber. It's again a 60 millimeter long fiber, but the 80 stands for length over diameter ratio of 80, which means that your diameter of your fiber is 0.65 millimeter, and we'll give it a dosage of 30 kilogram per cubic meter. The loads can be can give an input as the same as before. So we have a 120 kilonewton point load. The depth of the pallet of the racks is again 1 meter. You have a base plate of 120 by 120. This is the 2 points, so you will have it perpendicular to the edge, again at 30 centimeter. Oh, sorry. Also the 4-point load back to back. So 120, 120. This means that you have back to back very close to each other, 240 mm. It's a VNA, so the rackings are standing even closer to each other compared to the socket floor. So, and also, we'll see. And then make sure you see that you don't have a secondary joint tab anymore, which means that you don't have sockets anymore, which is indeed the case. So you cannot indicate this. So you will only place those point loads in the middle of the slab, perpendicular and next to your dilatation joint or your construction joint. So all those load situations are taken into account. For the wheel loads, we again go for the 1XL 2 wheels, which is your reach truck, which was a FL4, which is 45 wheel load, so axle load of 90, wheel pressure of 5 kilonewtons, can be located everywhere. And then you had the lorry with 2 very heavy axle loads at the back. So these are so 190 kilonewtons per axle divided by 4 wheels. Distance A is 20. Stays the same, and the distance between the 2 axles is a minimum of 1.2 meter. And the wheel pressure 2 can also be everywhere on your slab. Okay. Again, the UDL load, worst case, given 50 kilonewtons. And put it like this, worst case, because you don't know. The line loads will not incorporate. This can be, for example, if you have a rail system in your floor or some kind of non-structural walls which are casted on your slab, you can incorporate it as a line load like that. So now we have our first design. We'll go to see what the results are. So your initial design is always a bit based on your experience. We'll see here now that indeed you have point loads are too high or are exceeding your capacity at the punching check. So there's also something to consider, that we do as well bending as shear as punching is checked, as well as the soil pressure. So this is all taken into account in the calculation. Here it will be the punching because you have such a high point loads and only a base plate of 120 mm. Punching is the governing load case. And because it is next to your doweled profile, which can actually happen almost everywhere, you should think of what the best solution is. And in this case, I would increase the thickness of your slab, because otherwise it will be difficult to eliminate that punching close to the edge of the construction joint. So I've increased the thickness to 200 mm. Can calculate it again and see if the punching is okay. So you'll see you brought it back to 93%, which is indeed, you need to check that this is good. You'll see that the wheel loads and the UDL load in these cases are not governing anymore because of those high back-to-back point loads. So again, if you want to have the printout, you can again ask for it with an extended printout, press print, and it will be sent to your mailbox. I'll have it here with me. Again, you will see that everything is in there. All the thickness of your slab, the panel sizes, the panel size ratio, 2 layers of PE foil, the concrete clause and concrete dosage. This is all incorporated in this design note, together with the different load situations and the UDL load, looking for the worst case, which is an iterative way of calculating. And then again at the bottom, so this here you can find all the load cases that are checked. So as well, punching, shear, soil pressure, shear forces, as bending are all checked for the different types of loads you incorporate in the design. And then you have an overview again at the bottom. Okay, so look at the design. So what we have as a solution was a 200 mm slab, C2530, 30 kilo of 40/80/60, expansion joints, armor joints, every 40 by 40 meter, which can be a straight or a sinus or cosinus joint, and 2 layers of PE foil to minimize the friction, to make sure that there's no the shrinkage stresses are limited in your slab. As a last one, we can also do heavy duty pavements. I will show you this in the tool. This is an example of a port pavement, which we also have quite some references in, but here it is. These loads are always very high, and you're in an outside environment, so you will prefer to have sockets, but because sockets are very have a low load transfer capacity, you will probably need doweled joints. So this is also something you can incorporate in the tool. So if you go to a heavy duty pavement, you can select, if I go next, you can select at the structure, you can select dowel joints. So this is for heavy duty pavements. You can select them to make sure that you have a better load transfer at the locations of the sockets. This is a system we've used quite some time before, so it can be casted with steel fibers manually, or even with a paving machine, like you can see on the picture, and then you add the dowels to increase that load transfer at the sockets. You go to the, if you go to, for example, to the reach stacker, which has axle loads up to 1,100 kilonewtons and containers stacked 4 high. So point loads of 75 kilonewtons per foot plate. But because they are standing all close to each other, you have a load case which is very limiting and very governing. For example, like I say, it's 4 points in a rectangular. So where all the containers are stacked very close to each other, you can have 4 point loads in a rectangular at a distance of as close as 500 mm close to each other. So that are governing load cases that you can give in the design tool also, and do a check to make sure everything is there. I can show you what the so for these type of applications we mostly get also fiber-only designs, but instead of normal sockets, we have dowel jaw sockets of up to 8 meter by 8 meter, for example, in this case. But you don't have to place any mesh or reinforcement anymore, so it is a very quick way of constructing a port or airport pavement. We'll see. I'll show you also the wheel loads. So again, you have the very high wheel loads of the reach stacker of 275 kilonewton. In these cases, you need to make sure that, or you need to ask to the designer that it's not, when it's loaded, it doesn't drive over the edges, or when it does, that you also incorporate it, and make sure that you maybe place some additional reinforcement instead of making your slab like 300 or 350 mm thickness, just because of the governing load case of this type of vehicle driving over the edge. So I think these are the 3 demos I wanted to show. Torpong, I will maybe ask you if there are any Q&A at the moment, or if someone has some questions about the tool specifically, or some applications or features that you would like some more information about. Please put them in the chat so we can discuss them. Okay. Tom, you have any questions already? Oh, you're muted, Tom.
Sorry. Yes.
No problem.
We have 2 questions in our chat box.
Okay.
Yes. Let me. Okay. The first one is what is the factor do you use when converting mean strength to characteristic strength if standard beam test has 2 to 30% variation?
Yes. Okay. This is indeed a question. As I mentioned, this depends on the design standard. But for example, if you look at the Singaporean design standard, this alpha, wait, I will get the slideshow back there that I can show it, and share my screen again. Yes. So these conversion factors, alpha 1 and alpha 3, these are depending on the design standard or the norm you're using, are between 0.3 and 0.45. For example, for the Singaporean design node, this is for alpha R1, it is I think 0.37, and for the alpha 3 it is 0.42. So that really depends on what standard you're using. Any other questions, Tom?
Yes, another one. Okay, I would. Okay, for very high UDL load, like maybe 10 to 20 tons per square meter. Okay, if we choose the worst case model, the design solution result maybe with a very thick slab net and high dosage fiber. Yeah, okay, that's right. And there is no cost advantage under normal conditions. Can we choose the one block model in very high UDL situation?
Yes. Okay. Yes, that's possible. If you look at the UDL loading, so you can, if you have, for example, bulk storage, you can add this as a one single block, and there you can, for example, if you have 150 kilonewtons, you can add it like this with for example, a width of 10 meters. This can be added or can be defined in the system. So that's normally not a problem. Also, if you have, for example, big paper rolls or metal blocks stacked next to each other in different aisles, you can also do it with a single defined block where you have, if you have coils, steel coils stacked or placed in different aisles, for example, 5 meters wide, and with an aisle width of 2.5 meters, you can always define that based on the input you get from your client or from the design engineer. You can have choose this or can input this like you want. So that's indeed possible, even with high UDL loads.
All right, thanks for your input. Next, I believe is from our customer in Vietnam. He asking about generate tools template. It's
Yes.
only in PDF, right?
Yes, the reports are always sent to you via mail and will be in PDF. Yes.
And is it possible to have a Vietnam version or only just
No,
only in English?
no, it's possible to ask for a different language. Wait, I will take that off. If you calculated the results, example, and do next step, you here have the possibility to ask it in a different language. I don't know if Vietnamese is one of them, but they are a number of languages in which it is possible to request the design note. Yes. So I think
Okay.
if it needs to be Vietnamese, that's something we should take up with the salesperson in Vietnam to see if that's possible or not.
Okay, all right, thanks. And next question from the same guys. Have you applied the heavy duty pavement container yard with railway for gantry crane?
We have, but I believe in those cases the foundations of the gantry crane are done separately from the design of the port pavement, because those loads of the gantry crane are very specific and very high, and you need a high reinforcements, need large reinforcements over there. So in those cases, you have the design of the gantry who is separately from the design of your port pavement yourself. So in that case, you would only need to take into account the reach trackers that are driving over the floor, and then the design of the foundation of the gantry is separately.
Okay. All right. Next, I'm not sure. There is another specific question. They have a question about the earthquake up load uplift.
Yes.
Do you have any idea? I'm not sure the specific question.
Yeah. Well, for those type of questions, we will indeed. This is quite specific. The uplift earthquake forces. We can do that, but it's not incorporated in the standard tool. But that is something we can do. But we'll use a different like a nonlinear FEM model for that one. But we can do it, but it's not incorporated in our standard slab-on-ground tool. So indeed, it's in some areas in the world, the earthquake loads for racking systems are also uplifting forces. We can do designs, but it's not incorporated in this online tool. If you have some specific questions about it, you can just contact us for doing so.
Okay. Next question for about heavy duty pavement. Okay, normally for the saw cut joint, okay, do we have to use the dovels to install with the floor? But he means that dovels will increase construction difficulty. Yes. Can the saw cut joint without dovels solution to be applied for heavy duty pavement?
Yes, that can be applied, but in those cases, you will, depending on the loads that are put onto your slab, if they are too high, you will, those sockets or corners of sockets will become very governing load cases, and then your design will get, the thickness of your slab will become, quite thick. So it all depends on the loads of your containers. If you're only stacking 1 or 2 containers and your reach truck is, or your reach stacker is has not an axle load of 1000 kilonewton, I would say it's possible to do it without the dowels, but to have a cost effective and the most optimal design for heavy duty pavements where they stack containers up to 4 or 5 high, I believe you will need the dowels to make sure that that you have them. They have the most cost effective design. In some cases, we also did some seamless floors. So with the top mesh and steel fibers, then you don't need the dowels anymore. But in those cases, again, you will have to place the mesh. So it's not you will still need some manual labor for that one. Yes, I think still some questions.
Yes, he asked the two free for users.
Yes, so like I said in the beginning, if you go to the our CEP, you can press on discover the tool. I'm still logged in. You can just make a profile for yourself. So you can register. It's for free. And then if you want the advanced version, you can just put in a request, and then it will, depending on the country manager, he will give you access to the advanced version because it's only for engineers. So we will. That's why you need to request the entry to the advanced version, but it's free for everyone. And also this session is recorded, so the recording will be sent to everyone afterwards.